I use my 16 gigabyte, 16 or 8, I can't remember. 16. The 16 is my Linux, right? I use my 16 gigabyte Linux to play many games over, not man up, but hard coding the big array. A big array cannot go up to 2 gigabyte as described in this program because the index itself is a signed integer. And the signed integer, the mass value is 2 gigabyte minus 2 giga, not gigabyte. 2 giga minus 1. Okay, so we will have an overflow problem. So I transform the code into the following way. Break the array into parts. Okay, I don't allocate a 3 gigabyte array. I know that I will have a problem of overflow because of not using unsigned, but using signed integer. So I break it into parts and successfully gain all the memory. You can see while I show the top, the memory allocation keeps growing and hold that memory 4 gigabyte or 3 gigabyte, no problem, as long as you have enough memory. But I didn't try it in front of you. What happened if I try it on a 32-bit CPU? Okay, my previous show is a 64-bit CPU, which is my Linux. Now I have another Linux here, a VM. Okay, so whenever you touch a VM, you have to ask yourself questions. How big is your system? Okay, if your system don't have so many RAMs, you cannot go through this demonstration. So I have this command. You all have this command if you're using Linux. It's free. Free means a free memory or memory report. -m means display in terms of megabyte. Okay, so I just before I come here, I report this VM so that I allocate 4 gigabyte of physical memory to this machine. Okay, so it says 4 gigabyte. And now what I'm going to show you next is about this entry. Okay, the unit -a. Unix -a tell you that this is with this, it means the 32-bit CPU. Okay, so what I'm going to show you, first of all, try the 2 gigabyte again. Okay, but I only have the 3 gigabyte program here. Don't worry, I will modify that. Okay, I comment this C and comment this C. Okay, so let's do it. Global 3GB. Okay, compilation correct. Run. Now this, although I say 3 here, it says 2. Okay, you see my comments there. It's 2 gigabyte. No problem. Yeah. And now, previous case, if you have tried in your home or you are so afraid of that, okay, you try in your friend's home or friend's computer, okay, yeah, make sure that you try on a 64-bit CPU. It should be no problem. Now we go to the 32-bit CPU. What will happen? Okay, compile, no problem. Run. 64-bit CPU don't have this problem, right? I have a 64-bit CPU here. This is my Linux, Unix -a, 64-bit. Okay, still the same program. Okay, I know that you may not believe in me. Okay, so 1, 2, 3, 3 giga, run, no problem. Okay, what happened here? Is it because I have too few RAM? Okay, maybe not, maybe yes. Let's try something. Okay, let's try. How about I go back to the 32-bit CPU. I'm not so greedy. I change it to, let's say, 500. Okay, 2.5 gigabyte. So how about 2.5? Compile, no problem. Now you see the compilation always no problem, right? Only when it runs. Now remember, this time is 2.5. Huh? What can you say? What can you say? Take a look. So how can I set it? Okay, I set using size of. Okay, so whenever I change the size, it's okay. It seems that it can accommodate 2.5 gigabyte. Now, what do you want to try out? Binary search? Yeah, let's go to a 2.75. Okay, and so forth. Yeah, you don't know what's binary search? Yeah? Yeah, no, this time no need, okay? I'll fail you. Okay? Are you still good? Yeah, you try and tell me the limits, okay? And as a matter of fact, there is a kind of a limit there, right? When I try to tackle the system, I want 3 gigabyte, it stopped me with segmentation faults, okay? And actually, I don't know whether segmentation faults leave me any errors. And this is the what is called the dirty debug log. Okay, very dirty. So it's deep. No, okay. It's called a debug log from the kernel. The kernel never says anything about my program. It says all the whatever thing is not about my program. Yeah. So this debug log don't tell me that I have any problem, and I just been killed without any reason. Okay. And also take a look at the program structure. It seems that the segmentation fault is not coming from here, right? Just a start message. You print a start message and get a segmentation fault, no way, right? It seems the segmentation fault happens once you try to start the process. Understand my point? Understand my point? When you want to start the process, oh, it's ugly, yeah? Okay, good. So when you try to start the process, the entire system stops you, okay? And it's not because when you try to say start, okay, go on 1 GB, 2 GB, and boom, we don't have enough RAM. I just want to stop you. No, not this, okay? So what is the problem here? It's actually written in the notes. The notes already give you the reason. It's actually in 32-bit CPU we have a problem. 64-bit no problem. Okay, the problem comes from there is a space approximately 1 GB, approximately, it's not always 1 GB, okay? It's being reserved by the kernel. The kernel needs memory to work with, right? You have to allocate the space for the PID structure, for the scheduler to run, for whatever things, okay? It's actually reserved approximately 1 GB. I mean the space. Okay, so whenever you try to allocate a big process, you want to go for, let's say, close to 3 GB, it will stop you because you are touching its limit. So if you are far from 3 GB, let's say 2 point something, 2.5, 2.7, okay, it's still okay for you to go on with the creation of a process. Remember, it is time that when you try to fork and execute this program, the program says that, hey, I want that much of memory, the kernel immediately stop you. Okay? So this is quite strange error here. I think you will kind of unaware of it because nowadays you don't use 32-bit CPU. All people have 64-bit. So this will be getting outdated eventually. Okay, remember this, if you are playing with 32-bit CPU, okay, remember, although the address space accommodates 4 GB memory, in physical working, you cannot go on with a 4 GB allocation, including you're using malloc. Okay? So we go to something a little bit boring. What is a little bit boring? The stack. Okay? The stack itself, the mechanism is very boring. Okay, it's about where to put your local variable, where to put your program arguments, function arguments, and how it works when you call functions. Okay, and real fun come from the security course. The security course will ask you, not or ask you, me, teach you and also give you assignments in how to damage this stack so as to hack a program. Now, you get excited about this, right? Hack, okay, what is that? Okay, so first of all, I previously mentioned something, right? I mentioned several things, local variables, you know what are they, right? Function parameters, the parameters you try to insert in a function call and then pass to the function body, we call it a function parameter. What else? What are program arguments? What are environment variables? What are they? What are they? When you're trying to run the program, right? Remember, you can ask the outside world. Let's say that x minus L. Still remember, the minus L become an argument, okay? And actually, the argument is written here, right? You can get it as a string. And actually, these three guys, okay, the ARGC, ARGV, and this is the environment, are all hidden when you try to fork and execute the program. While we execute the program, you will be found these three guys in this area called stack. Okay, you may not find it interesting because you cannot see how it works. Okay, I just tell you, yeah, there it is. And the stack is very interesting. The allocation and deallocation, yeah. What is the meaning of deallocation and allocation? Allocation means you want to grow that range. Deallocation, you want to shrink that range. It's not done by the kernel. What's the meaning? The meaning is, here you want to make it bigger. You don't call malloc, okay? Calling malloc eventually calls system call. Now, what is the meaning of growing here? Growing here means that you call functions. Let's say you call functions, and I don't know why in your function you create an array, let's say 1 megabyte. Okay? Then that thing, the local variable, will put here and allocate some space. And what actually happened there, okay, is actually a compiler hard code. What is the meaning? The meaning is the compiler knows how the function works, right? You provide the codes, and then when you call it, okay, it will run those code without the awareness of the kernel. Maybe you don't know what I say. Now I go to the details. Okay, the details maybe you have heard of. If you have learned assembly, you must have heard of it. If you don't know what is assembly, yeah, this is the first time you will see something related. Okay, so what is it? The main. Okay, the main itself is a function, right? Maybe you don't know who called main. Okay, but main as a function, it exists, and the variables, local variables, all exist in the stack. Why we call it a stack? Here, it's called a stack. It's not because we join this way. Later on, you will see how it works and understand why it's called stack. And this stack, you will put the variables. Let's say the main contains 2 local variables. It is here. And what is the return address number 1 here? Later on, I will explain. Don't worry. Okay. And now, what the main function doing? The main function, the next step is a call function, right? Call a function called f1, and the f1 will call f2, and f2 will provide a return value, and that return value eventually propagate back to function 1. Function 1 return propagate the value back to function main. Okay. Now, how this works is when you call the function, this a and b guys will as if a stack, right? If you don't understand what is stack, it is too late. I cannot let you to lay drop. Okay. Push, okay? Push it there, and the order is not important. It's a system dependent, okay? Whether the system do this way or do this way doesn't matter. So that's why I created on purpose, okay? You don't need to remember the order unless you try to hack a stack, okay? Now this is the order. Let's say I push the 2 argument first, and then push the return address. So what is the return address here? The return address, later on we will see, and I illustrate it as a pointer, a function pointer or a code address. Okay, function pointer is the same as code address. The code address somewhere here. Okay, so what is the meaning of somewhere here? I will show you something which is imaginary. It is here. The assembly code, a rough assembly code, okay? It's not of an exact language, okay? But I just bring it up, okay? Now, what this function is doing before you call, you will try to push the value of A, push the value of B into the stack, and push the return address. So what is the return address? The return address is this instruction, okay? So what is the meaning? The meaning is, after you push this return address onto the stack, and you call the function f1, when f1 finishes its call, it wants to find a place to go back. right? I finished calling, okay? I should find a place to go back. This is the place. This is the place that you should go back, okay? And this is just a function, I'm not searching a function. It should be the address of the code, okay? Now remember this, later on it's very important point here, very important point, okay? Now let's say I finished pushing everything, now it's time to call the function now, I jump to the function, and these two locations immediately become the variable, what are they? The local, I consider them local, but you can consider this as an argument. The argument, u and v. Now can you see what is that? It is the truth, a true working of what is the meaning of pass by value, right? What is the meaning of pass by value? You push the values onto the stack and rename it, okay, as v and u. That's why the value is being copied in C in this one, okay? And actually, it is happening in all assembly languages. And what is this return address? We don't need to know yet. Now we will continue to call this function very easy. We will try to push the v and u together or to the stack. Now how to push the v and u? V and u already exists here, okay? But we still duplicate it as if we are copying a new copy of v and u. And the address which you try to return after you finish calling function 2. Let's say it's here. Let's say it's here. All right? So any question you want to ask yet? I think no, right? Because I didn't go back from the calling, okay? And then continue. We will change it into a function body, okay? Instead of some value being pushed down onto the stack. And because we create one more local variable, we will push one more value, C to 10 in the stack, okay? Now, the important moments comes. It tries to return, okay? It tries to return. We return x plus y plus c equal to 13. Now, how it returns is very interesting, okay? This rule only applies to integer. Let's say it is a floating point or return a structure. It's another complex work, okay? Now, for returning integer, it's very simple. You try to return, you will create these values and set the register value called EAX in Intel CPU and make it into 13. Make it into 13. Okay? And declare that, okay, I'm ready, I return. And where to return? Follow this return address number 3, go to this location. And continue to execute the remaining part of the function 1. Okay? Understand this point? You will copy the entire sum in the register value. So that means that here, this guy will know how to get the return value by reading EAX register value. Okay? Now this is only for integer. Structure, totally different. Our returning pointer is the same. Okay? Returning floating point is another complex problem. Okay? Now I continue. You continue to return. Why? Here is the return statement. So you will follow this return address number 2 to guide you back to the main. Guide you back to the main is here, right? And you still get that 13 because the return value 13 coming from here to here and then all the way go back to here. Now what's next? Next is this 13 copy to the variable b, which is also in the stack. Okay? So if you don't understand it, yeah, very simple. Yeah, go to buy a movie. That movie called Inception. Then you understand. Yes, you laugh, you understand why. Huh? If you don't laugh, by the way, do you know what is Inception? Yeah, do you need to show IMDb here? Yeah, Inception. Yeah, watch that movie, then you understand what is a function call. Okay, the function call is you are in the real world, call the city, and the city goes to the hotel go to the mountain. When you go to return, you cannot return back to the real world, right? You have to return from the mountain, go to the hotel, and the hotel, I don't know why suddenly there's a cake. The cake should be a folding exception. Folding exception go back to the city, and the city go back to the real world. Yeah, I remember it's very crazy. When I first see it in the cinema, I said, what? I'm studying computer science 101. Yes. Yeah, if you understand this like that, it's okay without the return value, okay? It's only function. I don't know what's the return value, okay? Don't forget that there is a stack, right? The stack of a scenario. Okay, this is a stack of scenario. Okay? Inception. So return 0. Last point, return 0. Now the return 0 is going to return to somewhere else from your main. Actually, it will return back to what we call a function hidden. It's actually hidden in the GNU C library. Okay, the C library actually contains the point to do all the garbage collection for you. So the return 0 actually means something. And also for exit. Exit is actually not an exit system call. Yeah, I faked you, okay? It's actually go back to the GNU-C library. Okay? So it seems that it's very boring, right? That's why I say this very fast. Yeah, pop, okay? And then, yeah, gone. What else we can play with? To play with this, how about we override these guys? Yeah. Did you ever think of we can override these guys? And do you know how to override these guys? Using pointers. Think about it. Go back to this program. If function 2 contains a pointer, and a pointer pointing to the address of C, okay, point to the address of C, then based on the address of C, can you calculate the location of this guy? Yes, you can do such a calculation, right? Maybe it is +4, maybe it is -4, but eventually you can find this location, override it. Override for what? Calling something you want to call. Yeah, in security course, people will try to override this return address so as to call shell. And the shell should be invoked by the privilege of roots. Okay, you call a function, and I don't know why the program belongs to root, and you can change permission to root, and want to execute with a shell with a root privilege, and then you suddenly gain the what we call privilege access. Okay, there's all kind of evils coming here. It's coming from this return address. So that's why Microsoft has so many bugs. It's written in C. It's because here, C allows you to change return address by careful calculation. Okay, in other languages you cannot do it, right? In Java, can you do it? No, you never know there is a return address. But in C, it's exposed to it, to you. Okay, the entire map. You can walk around there. Okay, you can try. Let's say that, okay, you know, I'm a naughty guy. Okay, I should prepare a program called play stack here. Okay, forget about this. Okay, so I can do the following. Pointer equal to address of I. Then what I want to do, I want to do the following. You know, I should be equal to 1. Okay? So I don't know. I just guess, okay? For maybe I do this. This is crazy. Don't do it. For j equals 0, j for maybe 100 times. Pointer plus j, dereference equal to 0. Do you know what I'm doing? First, I ask pointer to point to where? Point to the I variable. Okay? And if I do this, actually I can already override I, right? I can override I. Do you know what I'm doing? Okay, I don't have a loop. I don't have a loop, okay? PTR equal to 0. Okay, so first of all, you print I first time, you print I second time. Oh, what? Place that. Ah, yeah, wrong directory. Okay. So you can see I change, right? That means I can use a pointer to change somewhere in the stack. Of course, I can change many variables, right? If I know there is a array here, let's say the 100, okay, and I know how to calculate the step carefully and reach the array, then I can change the array using a pointer. All right? It's also in the stack. Also in the stack. So why not we cannot do this? Modify everything in the stack, including the return address, and ask the return address to return to something. Okay? And now this advertisement time. Take security course. Okay? I don't teach you how to do it. Okay? Or I'm actually telling 200 people how to hack. Okay? Yeah, take the security course. Okay? Security course teach you how to change it. Okay? Something more. The stack limit. Okay? Stack has a limit. What does the meaning of stack have a limit? Take a look here. Unit minus A. Unit minus A. So you can see stack size here. How big it is? How big it is? How big? 8192K. What is 8192? 8192 divided by 8, what is that? Yeah, use calculator, okay? Don't pretend that you're good at math, okay? Yeah, use calculator. I'm also bad at this, okay? I need calculator. Okay, let's use calculator. It's K, right? So that means 8K times K, 8 megabyte. Okay? The stack has a limit of 8 megabyte. That means what? That means, where's my program? Max stack. That means I cannot allow this program to run. Where's this program? I just copy this 8192 there times 1024. 8192 times 1024 is exactly 8 megabyte. And I just copy the ulimit statement. This is the limit. Now I create a limiting size here and try to memset it. Memset means set all the elements to be 0. Now I just want to make sure that where is the point that it fails if it fails. Okay. Okay, good to go. Yeah. Max stack. Good to go. Oh, no one tells me. Okay. Now what happened? Will we see start? No, not even start. You cannot even start because when you try to allocate that amount of stack space, you cannot do so. Okay? So how about this? Smaller. A little bit smaller. 8,000. 8,000K. Compile, still no problem. Run. Okay. Now, do one thing more. How about I create a function? Haha. Okay. And this haha function is doing some haha thing, right? 4,000. 1024. Okay. And I just copy and paste. Okay. Copy and paste here. Okay. So what I'm doing here, I want to tell you one thing. You declare some functions like this. Okay. Is there any problem? Now take a look here. When you add together, it is more than 8 megabyte, right? But I didn't call it, right? I didn't call it. So how the compiler will do, or how the system will do, let's see it clearly. Now, I didn't call it. Remember, I didn't call it. Compile. Run. No problem. If I don't call it. Okay, you can declare something big, but you didn't call it. Now, I call it. Haha. Okay. Compile. No problem. Do you know what is the moment that it got stuck? The moment is not because it knows the total allocation and boom, give it an error. It don't know the total allocation. You allocate for 8,000K, no problem, I give you, because I have enough space. Then I try to call the haha function. Oh, we need haha now. I should call it hi, okay. When you call it, you will try to expand beyond 8K, right? Then it is the time that you will get stuck. Now, do one thing more. That's why I call it haha, don't call hi hi. Okay. Go. You don't know what it says, okay. Yeah, we're computer science student, right? We know how to write recursion. I print start present d. I present d. I, and then I plus 1. So you will know for how many times it's called before it's dead, right? Oh, where? I have to what? Yeah, that's okay, right? I should be okay. Eh? 3 times. 3 times. Why 3 times? 8192, right? 8192. There is 40. 40 times 3, only 120. What are the remaining space? The remaining space go to somewhere else. Go to the environment variable. Go to the return address. Go to somewhere else being used by the library. Okay? So you cannot assume it's exactly 8 megabyte. It's fewer than 8 megabyte, but not that filled down to 7 megabyte. Okay? And now, do you understand what is stack overflow now? You understand what is stack overflow now? It's because you use up the space, not because you are calling too much recursion. Yeah, remember, someone cheat you, including me, okay? I teach people, oh, what is stack overflow, you call too much, okay? Yeah, this is just a convenient truth, okay? And not a truth, convenient false, okay? Yeah, convenience lies. Stack overflow means you use up the 8 megabyte stack limit. And yeah, this is the fun part about this course. U limit minus S is to change the stack size to somewhere else, to some value else. How about this? Good, okay. Too big, okay, disallow me. I make it bigger, okay? And let's see what happened. I don't know whether I need to compile. Let's say I don't need to. Ooh. Well, that means you can expand it. You think that you write a recursion in a perfect way, but you think that you don't have enough stack space. This is the way. Expand the stack. Okay? If you are guaranteed that you need that level, or you cannot think of another way to solve the problem without recursion, this is the way to rescue you. U limit minus S. Okay? And there, of course, are many other options. Okay? Many other options like minimize the number of arguments. Yeah. That's why I love to use global variables. Don't pass argument. Pass argument means you build up the stack, right? Fewer arguments, fewer stack space. Limit number of local variables. If your recursion need more number of local variables, that means again you build up the stack. You continue to build up the stack with fewer recursive call. Okay? And of course, you may think of a way to minimize number of call. Let's say that you use a for loop to call it 5 times in order to call 5 recursion. Okay? I don't know whether you can do it. Okay? So I think I should stop here. Of course, use global variable. I love it.